Okay, 12.1 is estimating limits graphically. So a limit is what values of f of x are approaching as the x variable approaches some value of a. So if we consider the function x squared minus 1 over x squared minus 1 over x minus 1, then we're going to factor this. And I basically want to know what happens at 1. So if I factor, I'm going to get x plus 1 times x minus 1 over x minus 1, which when I cancel these out means I have my hole here. And then what's left is x plus 1, which is a line. So I basically have a line with a hole. If I put this equation in the calculator and check out my table, for my f of x, I'm going to get 0, 1, 1.9, 1.99, and then it'll say error on the 1. That's because you have a hole there. If I check 1.01, I get 2.01, 2.1, 3, and 4. So you'll notice that as you're coming towards your 1, numbers are getting closer to 2. And as I'm coming the other way, I'm getting smaller towards 1. They're also getting closer to 2. So this function is discontinuous at x equals 1, because that's where I have a hole. And so what happens to my f of x as my x gets closer to 1, so the closer and closer I get to 1, the closer this gets to 2 from both ways. So your f of x gets closer to 2. And so then we can write this as your limit as x approaches 1, and as long as you're approaching it from the left and the right of the same thing, of x squared, sorry I'm making this so small, minus 1 for x minus 1, the limit is 2. And so in words, that basically says the limit as x approaches 1 approaches 1 of x squared minus 1 over x minus 1 is 2. Okay, there are 3 possible outcomes to a limit. Your limit doesn't exist, your limit exists and is a number, or your limit exists and it's plus or minus infinity. Sometimes when you have plus or minus infinity, they call that limit does not exist. Your AP calculus next year will take both of them for going to infinity. So technically, it has a limit. It's going to positive or negative infinity, but that's not really a number, so a lot of times we'll just say does not exist. So we can look at a table or a graph to find its limit. Note, the most important thing when solving for limits is that we only care about what's happening near the point, not what's happening at the actual point. So if it has a hole, I don't care what the value of that hole is. I care basically what's happening to the y values as I get closer to that hole. So a limit exists, limit as x approaches a number, exists if your limit as x approaches a to the negative. That means as you approach, I can't spell today, as you approach your x value from the left, from the left, and then this one with the plus means as you approach a from the right. So be careful those markings, whether it says a negative or a positive. That means from left and right. Okay, finding limits from a table. So I have the limit as x approaches 3 of 2x plus 3. I want to know, is the function continuous or discontinuous? And so the answer to this is it's continuous, because basically 2x plus 3 is a line, and no matter where I go, I am going to have an x and a y value. So it's continuous. And if so, where? So that's not, I don't have any words, discontinuous. Okay, if I plug in 2.99 into my x, 2.99, I want to look at x as it approaches 3 from the left. So I'm going to basically make my numbers get more specific and more detailed and closer to 3. So if I plug in 2.99, I'm going to get 8.8. If I plug in 2.99, I get 8.98. I get 8.998. So you can see as we get closer to 3, this is getting closer to 9. And if I actually plug in 3, I'm going to get 9. If I approach it from the left, if I plug in 3.001, actually let's start 3.1, I get 9.2. If I plug in 3.01, I get 9.02. And all of this I'm just doing on the calculator. This is just to get you to visually see what a limit is. And as I'm approaching 3 from the right, it's getting closer to 9. So as long as the limit you're approaching it from the left and from the right is the same, regardless of what this number is, that is my limit. So my limit is 9. Okay, example 2. I've got x squared minus 4 over x minus 2. Okay, I have x minus 2 times x plus 2 over x minus 2. This is kind of like our example on the first page. These will cancel, and I'm left basically with a hole and a line in it. So it's going to look something like this if you were to graph it. So if I plug it in, so this is discontinuous. And it's discontinuous where x is 2, because that's where my hole is. So if I put these in the calculator, and I put in 1.99 for x, 1.9, 1.9, 1.99, 1.999, I am going to get 3.9, 3.99, 3.999, and when I do 2, it should say error. That's because you have a hole. When I do it from the right, 2.1 gives me 4.1, 4.01, 4.001. So you can see from the left, it's getting closer and closer to 4. As I come from the right, it's getting closer to 4. So even though the difference between finding a coordinate and finding a limit is a coordinate would actually have a point, like for example up here this is 3, 9, whereas here there's no point. But the limit has nothing to do with whether there's a coordinate or not. It has to do with the behavior on the left side of that point and the behavior on the right side. So on example 2, from the left it's coming closer to 4, on the right it's coming closer to 4. So even though there's no coordinate at 2, my limit is 4, because from the left and the right, that's the number that it's approaching. Okay, next one, if you plug it in the calculator, absolute value of x over x, my limit as x approaches 0. You'll notice that it is discontinuous when you look at the graph at 0, because I can't have a 0 in a denominator. So if I go to my table of values, I'm going to get -1, -1, -1, error, 1, 1, 1. So from the left, my y values are all approaching -1, or they are -1. From the right, they're approaching 1. If I'm approaching a different number from the left and a different number from the right, basically, and I'm going to describe it in class, think of it like you're coming at a zit from 2 points. If you can come at a zit from the left and the right hand side and meet at the zit and pop it, there's a limit there. However, if I come from the left and come from the right, kind of like sometimes when they like stop you for, if they stop you for drunk driving and you try to put your fingers together, you can't meet. So there's that gap in there. So if they don't meet, then you're not poking anything, and that's the limit. So in this one, my limit does not exist. Okay, so then on example 4, these you're basically just going to look at a visual. So as my limit approaches -2 from the left, so here's my -2. If I want to approach it from the left, okay, you can see that my numbers are getting closer and closer and closer. My y values are getting closer and closer to 3. If I approach it from the right, those y values are getting closer and closer and closer to 4. So since I'm coming at the left to a different number and the right, they don't meet, my limit doesn't exist. Okay, so there's a difference between the limit from the left, limit from the right, and as x approaches -2. So if I just give you x approaches a number, you have to look from the left and from the right to make a decision. So when I look at the next one, my limit as it approaches -4, so here's -4. If I come from the left, my y value is getting closer and closer and closer to 2. If I come from the right, it's getting closer and closer and closer to 2. So as long as I come from the same thing from the left as from the right, that's my limit. Okay. On 5 from the right, okay, as I'm getting closer and closer and closer to 5 from the right, my x value is getting closer to 2. As I'm coming from the right, my y value gets closer to 2. My y value gets closer to 2, so my limit is 2. Okay, example 5. We're going to kind of do the same thing again. As I approach -3 from the left, my values are getting closer to -2. As I approach from the right, they're getting closer to -1, so my limit doesn't exist. As I approach -2, you'll notice that you have a hole here, an open circle, and a solid circle. Remember that this point is not going to have anything to do with your limit. This point is here just to trick you to understand if you know the difference between a point and a limit at that x value. So as my x approaches -2, my y values are getting closer and closer and closer and closer to 3. As I'm coming from the right, my values are getting closer to 3. A limit has nothing to do necessarily with the coordinate. So as long as I'm approaching the same number from the left and from the right, this point has nothing to do with it. So you need to be careful. On G, I'm approaching 3. So as I approach 3, oops, let me erase that. I need to make it smaller. As I approach 3, from the left, I'm getting closer and closer and closer to -3. From the right, I'm getting closer to -3, so my limit's -3. So I'm not always going to give you the numbers from the left or the numbers from the right. Sometimes I'm just going to give them to you, and you have to look at that. So this is where I'm looking for right now. And from the left and from the right, I'm approaching the same number. And it looks like it's about -1.5. Okay. 6, again, I'm just going to kind of go through these fast. Now, I don't have your limits from left to right at all. So at -4, you'll notice that from the left, it goes to -1. From the right, it goes to 0. So since there's a gap in there and those 2 points don't meet, your limit, does not exist. Okay, limit at -2. Okay, now I'm not always going to give you ones that are going to be easy. So this one I'm just going to kind of have to figure out. As I'm coming from the left and I'm coming from the right, I'm going to the same point. So I'm going to say this is about 0.3 maybe. I'm just going to estimate for right now. Next one. Limit as x approaches 0 is 0. Limit as x approaches 2 is going to be -1. And 3, I'm going to estimate that maybe about 0.5. And my limit at 4, what color haven't I used? Green. Again, you have a hole and you have a point. This point has nothing to do with your limit. My limit is -1 because both from left and right is going to -1. So it's -1, not -2. Okay, so let's talk about limits when you have asymptotes. Now keep in mind on this graph, you've got arrows on the ends of these. My program doesn't put arrows on them. So I want my limit as x approaches -3. So here's -3. So -3 from the left, if I'm going to the left, what's happening to these y values is they're getting smaller and smaller and smaller and smaller. They're basically going to -infinity. If I'm approaching it from the right, it's getting bigger and bigger and bigger and bigger and bigger and bigger. That's going to go to +infinity. So if I'm coming from the left and coming from the right towards this asymptote, and one's going to -infinity, one's going to +infinity, your limit doesn't exist. Okay, 8. So my limit as x approaches 1. So we're going to do this two ways. One way we're going to do it with graphing today, and another day we're just going to do with direct substitution, but I'm going to plot them for right now. So I'm going to do this one with blue. So that is a y, oops, let me make my pen bigger. This is a y-intercept at 1, up 2 over 1, down 2 over 1, down 2 over 1. Okay, so this is my graph, and my limit is at 1, so actually let's cut this one off. I want to go from 1, and it's an open circle, so let's make this an open circle at 1, oops, at 1, and that's part of that graph. This one I'm going to make green. So at 1, if I plug in 1, and I'm going to plug in 2, plug in 3, that gives me 3, 4 minus 4 is 0, 4 minus negative 9 is negative 5, or 4 minus 9 is negative 5. So I have a point at 1, 3, so you'll notice that basically now what was open is solid, 2, 0, 3, negative 5, and it's a quadratic, so it should be kind of curved. I don't draw very well, but that's my graph. So you'll notice when we did this one, there was no gap. The open circle here met with the closed circle here. They met on the same y value. So that one, if I want the limit as x approaches 1, as long as the value for 1 on the first function and the y value for the second one also gives you the same y value, then my limit in this case was 3. Okay, next one, we've got 3x minus 2. So 2 up 3 over 1, up 1, 2, 3 over 1, up 1, 2, 3 over 1, and I need an open circle. So here's my graph for this one. And then this is a parabola upside down. So if I start at 2, 7 minus 4 gives me 3, 7 minus 9 gives me negative 2. So at 2, 3, 2, 1, 2, 8. Hold on. Let me draw this graph a little bit better. It's hard to see. Let me do a thinner pen. Okay. So negative 2 up 1, 2, oops. Negative 2 up 1, 2, 3 over 1. Up 1, 2, 3 over 1. I'm trying to make this a little bit more exact. Okay. So now for the green, I'm here, and my graph is going to go this way. Oops. It's not a good graph. Let's try that again. So 3, 1, 2, 3, negative 2. So it's going to kind of curve. Ugh. I can't draw today. 1, 2, 3, negative 2. So it's going to kind of curve like a quadratic. So since my value from the left is approaching 4, but my value from the right is approaching 2, or 3, my limit does not exist at 2. 10, some of these you're going to have to put on the calculator. Some of these are asymptotes. So on this one, I'm going to do my parent function of 1 over x and move it up 3, which means I have an asymptote at 3. And so I have a point here, a point here. Oops, I also have a vertical asymptote at 0. This is my graph here. Oops, let me make this thicker. Okay, so my limit as I'm approaching infinity, which is this one. So as this goes, this gets closer and closer and closer and closer and closer to the asymptote. So it's going to get closer and closer and closer to 3. So when you have graphs with asymptotes, if you're going towards infinity or negative infinity, more than likely it's going to go to the asymptote. But we'll talk more about that later. Next one, my cosine graph. So cosine, remember, is 1, 0, negative 1, 0, 1, and it keeps going with that same pattern. So my graph basically goes up and down, and it keeps going in that same pattern forever. So if I'm going out to infinity, if this is going to continue to go up and down, up and down, up and down, is it going to have a limit? No, your limit doesn't exist because it's basically going to oscillate from up and down, up and down, up and down. So it oscillates and never approaches a number. approaches a specific number. Okay, my limit of sine of 1 over x. So if I put this in the calculator, this is kind of what it looks like. So this is one that I would just have to put in the calculator. So it kind of looks like this, and it goes da 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 da. Okay, so another place that you don't have limits is if you've got this graph kind of like sine was, where it's oscillating. Now, obviously, if I were to tell you as you're going to infinity, that might be different. But if I'm looking at 0 right now, it's going up and down. It's oscillating up and down. So my limit doesn't exist because I can't tell what it's doing. 13, my limit as x approaches sine of x. If I stick that in the calculator, this is about the graph. Oops. Let me erase those. So it's about here. This is not a graph I would expect you to know, but you can put it in the calculator. So if I look in the calculator, from the left and the right, it's approaching 0. So that's going to be my limit on this one. And that's the end.